According to the definition we have so far, this integral of a function f of x, when we talk about this integral, this function f of x must be defined on a domain that includes a bounded closed interval from a to b. Okay, so this is closed. That means the value of f of x must be defined at a and also at b. But if this function is not defined on this closed interval, but only in semi-open interval, like this, or like this, or even for open intervals, a, b, or something like a to infinity, this is unbounded semi-open interval, or even from negative infinity to positive infinity, then so far this our definition of integral cannot be applied to these cases. But we can extend the definition in the following way. For example, let's say we have a function f of x that is defined on this semi-open interval from a to b, including a but not including b. Okay, so the value of f at b is undefined. Okay, but we can define this integral from a to b of f of x as this limit. So t goes to b from the left, and this is the integral we have defined, f of x dx. Okay, so since this t is less than b, we are approaching this b from the left. So this function is defined on this interval from a to t. This is a bounded closed interval. Okay, so the domain of f includes this closed interval. So this integral is well defined according to our previous definition, current definition. So if this limit exists, okay, then we define this integral on the left hand side to be this right hand side. Okay, if this limit does not exist, then we cannot define this integral. Okay, and this type of integral is called the improper integral. So we can now define integrals for various intervals. Let's see. First of all, let's summarize the previous notion. So if f of x is continuous on the semi-open interval, let's see, a to b, including a, not including b, then we define this integral of function from a to b as this, b from the left and a to t and f of x dx, which is equal to this, epsilon going to 0 from the right, and a and b minus epsilon of f of x. Yeah, if this limit exists, then we can define this integral. Okay. In a similar manner, if f of x is continuous on this semi-open interval, then we define this integral to be this limit. Zero and a plus epsilon. And similarly, if it is defined on a to infinity, okay. By the way, infinity here is it's not a number, so we cannot include infinity like like this. But it is always open here. Okay. So in this case, we write not this. We write integral like a to infinity as this limit. T to infinity and a to t f of x. So by this integral, what we mean is this. Okay, if this converges, if the right hand side converges, and also we have negative infinity to b. So this integral from negative infinity to b, we mean t going to infinity and t to b. Okay. Let's see one example. Consider this integral from 0 to 1 dx over square root of 1 minus x. Okay, this function here, square 1 over square root of 1 minus x, it's not defined at 1, because if you substitute x equal to 1, then the denominator becomes 0, so it's undefined. So we calculate this as this limit. Epsilon goes to 0 from the right, and integrate from 0 to 1 minus epsilon. Okay. And the result is not that is negative 2 1 minus x square root, and this is, so if you substitute this, then we have negative 2 square root of epsilon plus 2. Wait a minute, we have limit here. So this limit is 2. Therefore, this integral's value is 2. Next, let's consider a function defined on an open interval from a to b. Then how do we define the integral? Like this. So what do we mean by this? To calculate this, we decompose this integral into two parts. So from a to c and c to b, where this c is any value between a and b. Okay, we just pick any arbitrary c, then split this integral into two parts. Then this function is now integrated from these semi-open intervals, right? C, a to c including c, and c to b including c here. Okay. Then we can apply the definition of the improper integral for semi-open intervals, and we are done. And similarly, we can also define the integral between negative infinity to positive and positive infinity like this. So we can split this integral into two parts. Then we have we can apply the definition of improper integrals for semi-open intervals. Let's see one example. So consider calculating this integral. -1 dx square root of 1 minus x squared. Okay, this function, this integrand, the function to be integrated, is undefined at both -1 and 1 because that will make the denominator equal to 0. So to calculate this, we split this integral into two parts. Okay, so let's split this into -1 plus epsilon and dx, and also 0 and 1 minus epsilon dx. By the way, this epsilon here in the first integral and this epsilon in the second integral, they are different quantities. Okay, they have nothing to do with each other. So although we happen to use the same symbol, they are just independent. So don't confuse. So we take this to 0, and also we take the limit to 0. Okay, and the first integral becomes arcsine x from -1 plus epsilon, and the second one is also arcsine from 0 to -epsilon, and if you put 0 here, then that should be 0, and then we should have arc sine -1 plus epsilon, and also arc sine 1 minus epsilon. Okay, and then we take the limit of each of these separately, and the first one converges to negative pi half, and the second one converges to pi half. So the result is pi. When I explained this integral, I said this epsilon here and this epsilon here, they are different epsilons. Okay, they're independent. To see this, to see why we have to differentiate these two epsilon separately, consider the following definition, alternative definition of improper integral, like this. Limit epsilon approaches 0 from the positive side, and a minus epsilon b a plus epsilon b minus epsilon. So how about this definition? Or for this integral from negative infinity to positive infinity, how about defining this as this? From minus t to t, we integrate this function and then put t to infinity. But this is wrong. Okay, so don't do this. To see why this is wrong, consider this example. So we want to calculate this integral. Okay, so according to our original definition, this is okay, so this is defined to be something like this. We split this integral. Okay, then we move each of this to these limits. Okay, so this t and this t, they are different t's, okay? So they move independently. So this would be limit negative infinity, and that would be x squared over 2 and t to c. C is any constant, okay? Infinity c to t, and that is c squared over 2 t squared over 2. And wait a minute, we need to take the limit. Okay, now this part is a constant, and if we move t to negative infinity, then the result of this term, the first limit, will be negative infinity, and the result of the second limit would be positive infinity. So negative infinity plus positive infinity is not equal to 0, by the way. It's undefined. This is undefined. We don't know what's going to happen. Okay, so undefined is the right answer in this case. However, if we apply this wrong definition, what would happen? Okay, so that would happen. So let's integrate from negative t to positive infinity. Then we have negative t to t. So that is t squared minus 2 and t squared minus 2. That is 0. But this is, this is a well-defined number. But this is wrong. So it's defined, whereas the correct answer is undefined. So this definition is wrong. So don't do this. Next, consider a function, let's say f of x, that is continuous on, continuous on this interval between a and b, closed interval, except for finitely many points. Let's say a1, a2, and an. So except for these points, this function f is assumed to be continuous. Okay, so then how can we define this integral of f of x from a to b? Okay, in this case, we can split this integral into many different, finitely many parts. So from a to a1, a1 is the first discontinuous point, and from a1 to a2, and a2 is the second discontinuous points, and so on. So up to an to b. Okay, then we can define each of these integrals separately. If all of them converges, then we can define the integral of on the left hand side. So that's how we can define the integral of a function that is continuous except for finitely many points. Now consider the following example. Suppose we want to calculate the integral of this function. x modulus square root in the denominator on this interval. Okay, so to calculate this, now this function is discontinuous at x equal to 0, as you can see. So this is, let's say, split into two parts, from -1 to epsilon. We are going to put this epsilon equal to 0. And let's see, dx square root of x modulus plus epsilon minus, I think minus should be put here because we move this quantity to 0 from the left. Okay, and the other improper integral is this. This time we use a different symbol here from this epsilon. We put epsilon prime here. Okay, anyway, so if we calculate this, that would be, since x is negative in this region, so epsilon, both epsilon and epsilon prime, they are positive. So that would be 2 square root of negative x, because x is negative. And here we have 2 square root of x from epsilon prime to 1. So that becomes, let's see, -2 square root of epsilon and plus 2 from the first integral. And from the second integral, we have 2 minus 2 square root of epsilon prime. And this converges to, each of these involving epsilon or epsilon prime, they converges to 0 as the epsilon and epsilon prime approaches 0. So the result is 2 plus 2, which is 4. So this is the value of this improper integral. In many cases, calculating the value of improper integrals can be very difficult, even if it's possible. In many cases, actually, it's impossible. I mean, at least analytically calculating improper integrals is not possible in many cases. But still, we may be able to decide whether an improper integral converges or not. So here's a theorem that gives you a clue. And let f of x and g of x be continuous function on a semi-open interval. Okay, and suppose the following. Okay, if the following conditions are met. 1. For all x in this interval, we have the modulus of x, f of x is less than or equal to g of x. And 2, the improper integral of g from a to b converges. Then this improper integral of f also converges. Okay. This is a kind of dominating function theorem, and we say in this case we are actually interested in this integral of f. But if we can find some other function, such as g of x in this case, then we can assure that this improper integral converges, if these two conditions are met. Okay, in this case, this g is called the dominating function of f. Okay, let's prove this. First, let's define two functions, f of t as this integral of t to b of f of x dx and gt in the same manner. Okay, now by condition 2, this condition, this function converges if we move t to a from the right, So let's see. So this limit t approaches a from the right and gt, so this exists. Okay, now let's use the Cauchy Criterion. Which we have learned in a previous chapter. So it's just restate this fact by using the Cauchy criterion. Okay. So for any epsilon that is positive and real, there exists some positive real number delta such that if t and s are in this interval between a and a plus delta, the semi-open interval, this implies g of t minus g of s is less than epsilon. Okay, so this is another way to say that this limit exists, okay, in terms of the Cauchy criterion. Okay, now using this expression, we can prove that f actually converges. Okay, f of t minus f of s modulus is equal to, by using the definition of integral, it's actually this is another way to express the fundamental theorem of calculus, f of x dx. So this is an integral from t to s. Okay, and then this is less than or equal to the integral of modulus of f of x. Now you should wonder how this inequality holds. Okay, you should try to prove this. Okay, so this is, in general, this holds true. Okay, so that is modulus of an integral is less than the integral of the modulus of the function. Okay, and now from condition 1, this is less than or equal to the integral of g over the same interval. Okay, the condition 1 was this. Okay, so the modulus of f is less than or equal to g of x. And now this is equal to uppercase gt minus uppercase s, which is less than epsilon. Okay, whether we put a modulus here or not doesn't matter. In any case, it's less than epsilon. Okay, so we have proved that this quantity is less than epsilon, where epsilon was any positive real number. Okay, therefore, again by the Cauchy criterion, this limit of f of t exists. So this means the improper integral converges. So this integral converges or exists. And that was it. Let's see one example of this theorem. Okay, so consider f of x to be sine x over square root of 1 minus x. And so we want to calculate the integral of this over let's see, from 0 to 1. Okay, we want to calculate this integral, but we don't have to calculate this integral to see if it converges or not. Okay, so here we are interested in the convergence of this integral. So to do that, to see that, we need to find a dominating function. In this case, let's say g of x to be 1 over square root of 1 minus x. Then this is a dominating function of f of x. So you should check sine x over square root of 1 minus x modulus is less than or equal to 1 over square root of 1 minus x. Okay, and I think hopefully this is easy to see. If you're not, if you don't think so, think harder. Okay, so now given that this g of x is a dominating function, the next thing we need to do is to see the integral of this dominating function converges square root of 1 minus x. But we already calculated this integral before as an example, and this was 2, so it converges. Therefore this integral of f of x, that is sine x over square root of 1 minus x, converges, without even calculating this value. We know it converges. The next corollary is a slight extension of the theorem. So let's write it down. And again, f and g are continuous functions on the semi-open interval a, b. And we are interested in the convergence of this improper integral of f of x. Okay, and this converges if the following conditions are met. First, for all x in this semi-open interval, g of x is positive. And 2, f x over g of x is bounded. On this interval. And 3, this improper integral of g of x converges. Prove this. First of all, since this second condition holds, there exists some constant real number such that for all x in this interval, f x over gx is which is actually equal to g of x, because g of x is always positive here, and this is bounded, so less than or equal to some constant real number. Let's call it m. So this means f of x is modulus is less than or equal to m times g of x. Now we can use this m times g of x as a dominating function of f of x. Then by applying the previous theorem, we can see that by the theorem, this improper integral converges. And we are done. Let's see one example. Suppose f is, as usual, a continuous function on this semi-open interval. And also assume that there is some real number k that is less than 1 such that f of x times this function x minus a to the power of k is bounded on this interval. Okay, then we know that we can say that this improper integral converges. Why? So this is an application of the corollary, and if we define g of x as this part, actually the inverse of this part, x minus a to the power of negative k. Okay, and since k is less than 1, negative k is greater than or equal to negative 1. So this means this integral, this improper integral converges, as we have seen before. Okay, so we apply, so that means f over g is bounded. Okay, so f over g becomes f x times x minus a to the power of k, right? So we're assuming that this is bounded. Okay, therefore this improper integral converges. You should notice the beauty of this argument. You know, we don't even have to know what this function f is, really. All we have to know is that this is bounded. That's all we need to know. So as long as this condition is satisfied, f of x could be anything, any function. Satisfying this, we know that it converges. Now let us see a few examples of integral calculus. The first example is how to measure the length of a curve. So a curve is something like this. So how do we measure the length of this curve? So to formulate this problem, we consider, so this is a curve in two-dimensional space, okay? So we consider two functions, x of t and y of t, okay? And this will be the x coordinate of each point in this curve, and this will be the y coordinate of this curve. And t varies from from a to b. Okay, so this is a closed interval. And we also assume these are C1 class. Okay, this means they are differentiable at least once, and the derivatives are continuous. Okay, this is the C1 class. Okay, so let's see. This is point P and this is point Q, and this corresponds to x of A and y of A, and this the endpoint corresponds to x of B and y of B. So as t, this value of t moves from A to B, the point moves on this curve like this in this example. Okay, so how do we calculate this? So one idea is, although we don't have any formula for the curve, we have a formula for calculating the length of a line segment by using the Pythagorean theorem. So for example, just take a few points on this curve and then draw straight lines, connect straight lines here, 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 and here. So then we can calculate the length of each segment here, right? Then we take even finer, more points on this. Then we can refine the length of the line like this. So like this, and this. So if we take infinitely many points along the line, then the sum of the lengths of these line segments will approach the length of the curve. So that's our estimate. Okay, so based on this idea, let's formalize this problem. So first, we put some points along the line. So that will be called a partition of this interval. Okay, so let's call this partition delta. So A we would call T0. Then we take T1, T2, and so on. And Tn minus 1, Tn, which is equal to B. Okay, so these points will constitute this partition delta. Okay, so we have these points P0, that is x of T0 and y of T0, which is actually P. Okay, so this starting point. This starting point, and P1 would be x of T1 and y of T1. Okay, and we have Tn x of Tn, y of Tn, which is equal to the endpoint here. Okay, now we can calculate the length between P0 and P1 based on the Pythagorean theorem. So that would be square root of x of T1 minus x of T0 squared plus y of T1 minus y of T0 squared. Okay, so that would be the length between the first 2 points, P0 and P1. And we can do this for any consecutive pairs of points. So in general, we have I plus 1, Pi, as x of Ti plus 1 minus x of Ti squared, and y of Ti plus 1 minus y of Ti squared. Okay, so let's add up all these lengths of segments. Then that we call L delta, length of this partition delta. So that will be the summation I from 0 to n minus 1 of these square roots. So x of Ti plus 1 minus x of Ti squared, and y of Ti plus 1 minus y of Ti squared. Okay, and we apply a little trick where we divide everything by Ti plus 1 minus Ti. So that will be, let's see. So let's see this part. let's put this part again, and we divide it by ti plus 1 minus ti and multiply by the same factor. Okay, so that won't change the summation, okay, because this and this will cancel. And then we put this inside the square root. Okay, then this will be equal to, let's see, again, let's paste it. Oh, no. Let's see. And let's see. So we put this one inside the square root, so it will be squared. Actually, we split this and divide this by t plus 1 minus ti and everything squared. Okay, and ti plus 1 minus ti and everything squared. Okay, so everything square root and times ti plus 1 minus ti. Okay. Now, look at inside this. Look at inside this and this. Okay, and we can apply the mean value theorem. So in each subinterval, there exists some Si and Si prime in each subinterval, Ti and Ti plus 1, such that derivative of x evaluated at Si is equal to x I plus 1 minus x ti over x ti plus 1 minus x ti. And also the same thing for y, s prime. Okay, so there is some Si and Si prime, so here and here, that satisfy these equations. Okay, but we are assuming that y is of class C1, and of course so is x. So that means this derivative is also continuous. Not, it's not just a derivative, it's also a continuous function. So the difference between this one, y dy dt of Si prime, is almost equal to this. Okay, actually, as the mesh of this partition decreases, this one, the left hand side will converge to the right hand side. Okay, so they will be the same thing. Okay, so if this delta is refined, we can replace this s prime with s. So we just approximate. So we simply replace this with this. Okay, in this expression. So this one is replaced with this, and this one is replaced with this. So in that case, this L delta becomes this simplified expression. So square root of derivative and Si squared and d dt and y si squared and times ti plus 1 minus ti. Okay. Now let's define a function h of t by this. So actually inside this at this square root. So x of t squared okay. In this summation here, this si and s, these si's are some constant within each subintervals. So, but here we generalize this as a function of t. Okay, here we have t. It's a function. Then let's see. Then we define this mi to be the minimum of this function ht, where t is between this closed subinterval. Okay, we're assuming x and y are continuous and also their derivatives are continuous. So we can define this minimum and maximum. Okay. It's not just supremum or infimum. So using these values, we find this inequality. Okay. Instead of this value of square roots, on the left hand side, we have lowercase m times this length of interval less than or equal to L delta, which is less than or equal to this uppercase mi times the length of the subinterval. Okay, you've seen something like this before, right? This was used in the definition of the Riemann integral. So basically, this one on the leftmost side is the lower Riemann sum, and this rightmost side is the upper Riemann sum. And if we refine this delta, then both sides converges to the same value. That is just the integral of h of t dt, right? So this was just the definition of the Riemann integral. So it makes sense to define the length of the curve as curve C as this. Okay, that is the integral from a to b of this function, derivative of x of t squared plus derivative of y squared dt. So this is how we can calculate the length of a curve. Let's see a simple example. In this case, suppose x of t is r cos t and y of t is r sine t. Okay, and we assume r is positive and t is between 0 and 2 pi. Okay, if you plot this, it's just a circle. Okay, so this is r. So this is a circle centered at the origin. Okay, so what we are doing here is to try to calculate the length of the curve. So that starts from here, so t equal to 0, and goes around the circle and stop at t equal to 2 pi. So that is the length of the curve, which you already know to be 2 pi r, right? So let's confirm this by applying the method we have just described. So the length of this curve should be given by this integral, 0 to 2 pi and square root of x prime of t squared, maybe I should write it like this, plus y prime of t squared dt. Okay, it's ugly, so let's erase it. So x prime, so derivative of x is minus r sine t, and y prime, the derivative of y is r cosine t. So if you substitute this in here, the length of the curve is r squared sine squared t plus r squared cosine squared t. dt. And if you factorize r squared and put that outside the square root, we have r, but then we have sine squared plus cosine squared, which is 1. So this is the integral we have now, and there's no t, so it's just r times t from 0 to 2 pi, which is just 2 pi r. The next example is the cycloid, which is a cycloid, which is defined by these equations. T minus sine t, and y of t is a times 1 minus cosine t. Okay, and this a is a positive number, positive real, and t moves in this range between 0 and 2 pi. Okay, and it will look like something like this. Okay, so something like this. So depends on the value of a. So this point and this height and width may vary, but more or less like this. Okay, and let's see. So x prime, if you differentiate it, it will be a 1 minus cosine t, and y prime is a sine t. Yeah. So the length of this curve is given by, so just square it and add them and take square root. So from 0 to 2 pi, and 1 minus cosine t squared and sine squared. And a squared is moved outside already. So this will become, so if you expand them and use some formulas to get rid of sine squared and so on, and we have 1 minus cosine t. And then we use some formula to reduce this to 4 sine squared t over 2. And by changing variables, this becomes from 0, wait a minute, this is 2 pi, and then this becomes pi and sine u du. So we changed the variables from t to u somehow, and this will be 8a. Okay, and from here to here we have used the formula which you should prove, 1 minus cos t over 2. Okay, so this cos t was replaced with this sine squared, 2 times sine squared t over 2. The use of integrals is not limited to calculating the area under the curve or the length of a curve. It is also used for defining new functions. Here we see an example by defining the function called the gamma function. Let me just give you the definition first. Okay, gamma function, or gamma of s. So this is the Greek letter gamma, which is the capital letter, and the lowercase is this. Anyway, so this is defined as an improper integral of this function, negative x and x to the power of s minus 1 dx, where this s is, the domain is between 0 and infinity, not including 0. Okay, so positive real number. However, for this definition to be meaningful, we first have to show that this improper integral actually converges. So that's what we do next. Okay, so let us provide this as a lemma. Okay, so we can say gamma function is well defined, or we can say for any positive real s, the improper integral from 0 to infinity, exponential negative x, x to the power of s minus 1. This converges. So this is a lemma. Okay, let's prove this. To prove this, we split this integral into two parts. Okay, one is 0 to 1, and 1 to infinity. Okay. Let's define this integrand as a function. Okay. Okay. I think it's easy to see that the first integral actually converges. The problem is the second one. But anyway, if I say it's easy, you should really check if this really converges. Okay. And so let's see the second part. Okay, so we consider this, first consider this function f of x times e to the power of x over 2, which is, wait a minute, x to the power of s minus 1 over e to the power of x over 2. Okay, and let's take a natural number n. So take n such that n is greater than or equal to s minus 1. Okay, then we have x to the power of s minus 1 over ex 2 less than or equal to x to the power of n over e to the power of x over 2. Now, by applying L'Hopital's rule n times, we can show that this converges to 0 as x goes to infinity. Okay, and so this function is bounded in that case between above x greater than or equal to 1. So this means the left hand side is also bounded, of course. Therefore, by a previous theorem or corollary, we can say that this integral converges. And therefore, the gamma function is well defined. Next, let's summarize some of the properties of the gamma function as a theorem. Okay, so for any s greater than 0, gamma function is positive. So that's one. And second, for any, let's write it like this. For all s greater than 0, gamma s plus 1 is equal to s times gamma of s. And 3, for all natural number, any natural number, gamma of n is n minus 1 factorial. Okay, let's prove this. The first one should be trivial. From the definition of gamma function, it cannot be negative. So 1 is trivial. And second one, how do we prove that? We apply integration by parts. Okay, by integration by parts. So gamma of s plus 1 is, so just apply the definition here. Then we have x to the power of s dx. Okay, then apply the integration by parts. We have, let's see, so we have exponential here. So just integrate this. We have negative and x to the power of s, 0 to infinity, and minus, but we have a negative sign here, so it would be positive, and 0 to infinity, and e to the power of x, negative x, and derivative of this is s times x to the power of s minus 1. Okay, and then this part, the first part, if you calculate this, it will be 0. As we have seen, this, okay, any powers of x divided by exponential function will converge to 0 as x goes to infinity. And when x is 0, this is 0. The second factor is 0, so of course it's 0. So in any case, it's 0. So the first term disappears. And what's left is the second term, which is s times this integral. So this s is put outside by the linearity of integration. Then we have this, which is s times gamma of s. This is just the definition of the gamma function. Okay. So that's the proof of part 2. And for part 3, so from part 2, for any natural number n, we have gamma n plus 1 is equal to n times gamma of n. Just replace s with n, and that's it. So, and we calculate gamma 1. Okay, that is, if you substitute s equal to 1, we have, by definition, this. So the power of x disappears, and if you calculate this, this is just this, and that is when infinity, this will converge to 0, and when 0, this is 1. So negative minus negative 1 is positive 1. So we have 1. So that is so let's start from we start from gamma 1, then gamma 2 should be 1 times, so we can use this formula. So 2 is 1 plus 1, so 1 times gamma of 1, which is 1. And gamma 3, which should be 2 times gamma 2, which should be 2. And gamma 4 should be 3 times gamma 3, which is 3 times 2, which is 3 factorial. And you can continue this. So n plus 1 should be, if you want to do this more rigorously, you should prove by mathematical induction. But I think this should be easy enough to see. So the proof is done. And gamma function has some practical applications. For example, in statistics, we have a distribution called gamma distribution. As the name suggests, this distribution is characterized by a gamma function. In general, if some function has a name, proper name, like gamma function or beta function, as we will explain next, they should have some practical applications. Our last example is the beta function. Let us give the definition first. Okay. So beta function is actually a function of two variables. So beta. So this is just b, capital B, right? But it's also the capital letter for beta in Greek. Okay, so it's a function of two variables, p and q, and it's defined by this integral x p minus 1 and 1 minus x and q minus 1 dx. So these variables p and q appears here and here, and the domain is this p greater than 0 and q greater than 0. So all positive real numbers. Okay, of course, for this definition to be meaningful, we have to show that this integral actually converges. First of all, you should understand why this integral is improper. Okay, when p and q are both greater than 1, then there is no problem. This is just it's a proper integral. However, when either p or q is less than 1, then one of these terms can diverge, right? So this when p is less than 1, for example, if you put x equal to 0, then this will diverge. When q is less than 1, but still positive, of course, between 0 and 1, then this term will diverge when x is exactly equal to 1. So we have to evaluate this integral as an improper integral. So let's prove that this indeed converges. Okay. To do that, we split this integral into two parts. Okay. First, let's define f of x as the integrand. Okay. P minus 1, 1 minus x, q minus 1. And then split the integral to two parts, 0 to 1/2 and 1/2 to 1. Okay, Then first consider this one. Okay, for this closed interval, we calculate f x is in this interval, f of x times, actually we should try x over, let's see, f of x over p x to the power of p minus 1, which is f of x and x1 minus p, which is, so we eliminate this first factor, we have 1 minus x to the power of q minus 1. And in this interval, this function is bounded, right? There is no divergence here. Therefore, by previous corollary, the function f of x can be integrated in this interval. Okay, so this one converges. And when x is in the other half, then we consider f of x over 1 minus x q minus 1. So which is x to the power of p minus 1. Now, in this interval, this function is bounded, right? There is no divergence. Whatever the value of p, as long as p is positive, then there's no problem. It's bounded. Therefore, this integral converges. So either way, so both integrals converge, so we can define the beta function with no problem. Let's summarize some of the properties of the beta function as a theorem. So 1, for all p and q which are positive real numbers, we have beta p q positive. This should be trivial from the definition. And second, we have beta pq is equal to beta qp. So it's kind of symmetric function. And third, beta p q plus 1 is equal to q over p beta p plus 1 q. So let's prove this. The first one is trivial, so I'll skip it. And second one, we change variables. We define t equals to 1 minus x, so b p q, which is defined as this, q minus 1 dx becomes, let's see, so when x is 0, t is 1. When x is 1, t is 0. And x becomes 1 minus t, and p to the power of 1, and 1 minus x becomes t, and q minus 1, and dx becomes negative dt, right? So we swap this lower bound and upper bound by adding the negative sign, so it becomes 0, 1, and negative sign disappears, and we have t q minus 1, 1, t p minus 1 dt. But of course, the symbols used for integration, it doesn't matter, so this is the same as beta function of q p. And we're done. And for the third part, let's try integration by parts. And so first we multiply this beta function by p, and this is p 0 1 x p minus 1 1 minus x. Here it's cube plus 1, so the exponent is cube. And now we apply integration by parts. Let's see. So p times this is the derivative of x to the power of p, right? So this is equal to x to the power of p, and this one q, and from 0 to 1. And minus this, and there's minus sign here, so it's actually positive. And that becomes, if you differentiate this, q minus 1 dx. Negative 1 cancels this negative sign, so it's positive here. So put this q out, and this first term disappears, right? So if we substitute 1 here, now we have p and q both positive, right? So there's no problem if we substitute 1 and 0 here. So both become 0, so it disappears. And this one, q x p 1 minus x q minus 1 dx. So this one is beta p plus 1 and q. So we are done. Let's see one example of the beta function. Let's say a and b are real numbers greater than negative 1. Then we have this integral, 0 to pi half sine to the power of a, not x, let's say it's theta, and cosine to the power of b theta d theta. This scary integral can be calculated as 1/2 beta function a plus 1 over 2 and b plus 1 over 2. So how do we do that? So in the definition of beta function, pq, and this integral, that is x p minus 1 minus x q minus 1. So in this definition, let's do some substitution. So let's put x equals to sine squared theta. Then dx is 2 sine theta cosine theta d theta. Okay, and when x varies from 0 to 1, then theta varies from 0 to pi half. Now we can make bijection between x and theta in this way. Okay, so therefore integration by substitution, we put this x into here. Instead of x, we use sine squared. Instead of dx, we use this. So this integral of beta function becomes bpq becomes, so when x is 0, theta is 0. When x is 1, theta is pi half. And sine 2 p minus 1 and theta, and cosine squared q minus theta, and times 2 sine theta cosine theta d theta. Okay. Now we put x equals to sine squared theta. So 1 minus sine 1 minus 1 minus sine squared theta is cosine squared theta, right? So this part becomes cosine theta, and that's this part. Okay, and this comes from dx. Okay, so let's arrange this a little bit. So sine theta appears here and here, cosine theta appears here and here. So that will be sine to the power of 2p minus 1 theta times cosine to the power of 2q minus 1 theta d theta, and we have this 2 out. Then we put 2p minus 1 equal to a and 2q minus 1 equal to b, and we are done. Okay, that's all for today. See you next time.